In this lecture, we'll be addressing the issue of applied optimization. So a general optimization problem is asking you to maximize or to minimize some quantity. So given such a problem, the first thing we need to do is to identify what quantity you're trying to minimize or maximize. Once you have that, you also have to identify your independent variable. And we express the dependent variable as a function of the independent variable. That's the objective function. That's the function that will be either minimized or maximized. In addition, we should identify the possible values for the independent variable. So the domain of the objective function. The domain in question with this problem at hand. Typically, we have a closed interval for that. So for instance, if you're maximizing profit, maybe some kind of input, you typically have, say, 0 to some number of pounds of an input. You typically don't have the whole real line being the independent variable, the range of values you can use. It's not always the case, but it's often the case that we're working on closed intervals. Once we have that, find the critical points of the objective function. Identify the extreme values of the objective function. If you're working on a closed interval, you check the endpoints. And then answer the question. So this is really an applied version of the differential calculus approaches that we've already taken, or learned about in this course. So let's look at a couple examples. First, let's look at an area problem. Let's find the maximum possible area of a rectangle with perimeter 200 meters. You could think of this like you have 200 meters of fence, and you want to build a fence for a garden to keep rabbits out from eating whatever you plant. But you want to use your fencing so that you can get the biggest possible crop yield, which would mean the biggest area of the garden. So let's translate the problem into a mathematical model. So first, we of course know that our garden has a length and a width, since it's going to be rectangular. And we know that the area is the length times the width. And oftentimes in these questions, you use the information to reduce your function to have only one independent rather than two independent variables. And in this case, we notice that there's a relationship between W and L. Specifically, the perimeter has to be 200 meters. So we have 2 times the length plus 2 times the width is 200. This is, of course, nothing more than summing up the lengths of the sides of the rectangle to get the perimeter. If we divide by 2, we get L plus W is 100, or solving for L is 100 minus W. We can then plug that into our area function, and we get area as a function of W is 100 minus W times W, or 100W minus W squared. So this is our objective function. So now we want to optimize this objective function. And the natural question is, first, what are the values, the fair game values we could plug in for W? Well, note, what's the biggest W could be? Think about shrinking L down to 0. In that case, you could think of a very tiny L, so you would have a very long and skinny garden, in which case you're getting close to W plus W. And so as this gets skinnier and skinnier, then your W is approaching 100. So it's natural to say that W is between 0 and 100. If W was 0, it would be the reverse of that picture. It would be a very tall and skinny rectangle, where your width is shrinking to 0. So this is a natural set of choices for the width W. And now what we want to do is maximize this area function over this closed interval. So the first thing we do is find the critical point. So a prime of W is, so differentiating our objective function, 100 minus 2W. We set that equal to 0 to get the critical points, which gives 100 equals 2W, or W equals 50. Now we know this is a continuous function on a closed interval, and we know that its maximum value has to happen at either a critical point in the interval or at the endpoints. So we need only check these 3 points. So if we plug in a of 50, we get 100 times 50 minus 50 squared. This gives us 5,000 minus 2,500, or 2,500. And then in the other cases, notice you get 0. If we plug in W is 100, this term is 0, so we get 0 for the area. And if we plug in 0, this term is 0, so we get 0 for the area. So this means that we have found the maximum. So the maximal area is achieved with a square garden. So the width is 50 and the length is 50. Now this is one way you could have done this problem. Another way you could have confirmed that this is a maximum. So an alternative, if you hadn't checked that W should live in this interval, you could have said, well, let's think about a double prime. If we take the second derivative, we just get minus 2. Now this is negative for all x in the real numbers. And if you remember our second derivative test for global extrema, this means since W equals 50 is the only critical point, and F is concave down for all x in the reals, this is the global maximum. And if you remember, the idea there was that if your function, in this case, we had this one critical point at W equals 50, and we have a horizontal, only one horizontal tangent line, so one critical point, and it's concave down on the whole real line, then what we found here was the global maximum. So this is another way you could argue this. Now, either way is fine, but it's important to make one of these kinds of arguments to show that you have in fact found a maximizer. Because up until we actually either checked the endpoints or checked the concavity, all we had done was found a critical point. And a critical point of an objective function could be a minimum, could be a maximum, could also be neither. So it's important to do both steps in an applied optimization problem. Let's check another. Let's do a volume problem. Now let's find the maximum possible volume of a right circular cylinder if its total surface area is 150 pi square centimeters. One way you could think of this is that you are maybe a factory that cans soup, and you want to figure out that if you have 150 pi square centimeters of material for each can, maybe based on some piece of machinery that's giving you this material, what's the biggest can in terms of volume that you can produce that uses this to make the surface of the can? So the first thing we want to do is draw a picture, get an idea of what's going on. Right circular cylinder means what we think of as something like a soup can. And we usually say the height is h, and then we look at the radius of the base or the top. And remember, the way we get the volume of a can, it's the area of the base or the area of the top, which the top or the base is a circle. That area is pi r squared, and then multiplied by the height. It's just like if you think about the area of a cube. The area of a cube is the length times the width times the height, but you could think of the length times the width as the area of the base. So length times width times height can be interpreted as area of the base times the height. Here we have the same idea. We're taking the area of this base, which is the pi r squared piece, and multiplying it by the height. Now, as in the previous example, we have two independent variables here, and we need to get rid of one of them. And we know we're given a constraint on the surface area. So what's the surface area of the can? Well, the surface area of the can will be the area of the base, specifically twice that, because you have a top and a bottom. And then you have to add the area of what we'll call the side. Now the area of the base, that's a quick one. We've already argued that that's pi r squared. So this will be 2 pi r squared. Now for the area of the side, it will be the height, and then think of taking that height and wrapping it once around. So we need to take the height times the circumference of this rim here. So the circumference of the rim is 2 pi r, and the height is h. So that's our surface area, and our constraint says it must be 150 pi. So this will allow us to get rid of one of the variables. And it's up to us. We can get rid of h or get rid of r. Looking at this, it's going to be easier to solve for h than it is to solve for r. This is quadratic in r and linear in h. So let's solve for h. So we get 2 pi r h is 150 pi minus 2 pi r squared. And then we can cancel some things. So we can cancel the pi terms. And we can divide by 2. So we divide this whole thing by 2r to get that h equals 75 minus r squared over r. And this will build into the problem that the area of the can has to be 150 pi. So building this in, this means the volume as a function of r come back up to our equation for volume. We have pi r squared times h, and we are now replacing h with this quantity 75 minus r squared over r. And this simplifies a bit. One of the r terms cancels. So we get pi r times the quantity 75 minus r squared. Multiplying through, we get 75 pi r minus pi r cubed. And so this is our objective function. We then take its derivative with respect to r. We get, for the first term, 75 pi, and then we get minus 3 pi r squared. So we have our derivative, and now we move to the optimization phase. So the first thing we do, and remember, we can do this a couple ways, but we can check our endpoints. So our endpoints, what are the natural values for r? Well, we could make a perfectly flat, or I should say, a radius 0 can. So a can that's actually just like a really skinny pole. That would have, remember, our volume is pi r squared h. In this case, that would be v of 0, which would be 0. And then the other case would be the case where you have just a flat disk. So you would have the case where you have a 0 height. And remember, height was 75 minus r squared over r. So this would be 75 minus r squared over r equals 0, or 75 minus r squared equals 0. R squared is 75, or r is the root of 75. We wouldn't use the negative square root of 75 because we're not building a can with a negative radius. And in that case, the volume is pi, again, pi r squared h. Well, we derived this by doing a can with a height 0, so we see the volume is also 0. So if we make our chart, we have natural choices for the radius. Being between 0 and root 75. And so now our problem is reduced to maximizing our function on this interval. So that's the first part. Now we can check for the critical points. And so we have v prime of r equals 0, or 75 pi equals 3 pi r squared. We can do some cancellation. So the pi's cancel. Dividing by 3 gives us r squared is 25, or r equals 5. Again, we don't use r equals negative 5. It's not in this interval. Physically, it doesn't make sense. Let's check the volume. V of 5, remember our function, v of r was 75 pi r minus pi r cubed. Thus, when we plug in 5 for r, we get 75 pi times 5 minus pi times 5 cubed, or 75 times 5 will be 150, 300, 375 pi. 5 cubed is 125. And so this gives us 250 pi. And so this is our optimal radius. We have a maximized volume of 250 pi square centimeters. And if we want to say what the height is, remember our height was 75 minus r squared over r. So in this case, if we wanted to call it h star to be the optimal height, that would be 75 minus 5 squared over 5, or 75 minus 25 over 5, or 50 over 5, or 10. So our optimal can, our maximum value can, has a volume 250 pi square centimeters, a radius of 5 centimeters, and a height of 10 centimeters. Now, alternatively, we could have checked that this was a maximizer, again, with a second derivative test. So, once again, alternatively, we had v prime of r was 75 pi r. No, sorry, that was v. 75 pi minus 3 pi r squared. If we take the second derivative, the derivative of this constant term is just 0, and we have a negative 6 pi r. Now, we can easily argue that r has to be greater than or equal to 0, because we're not dealing, again, with cans of negative radius. So for r greater than or equal to 0, v double prime of r, if we're plugging in something greater than or equal to 0 for r here, we're getting something less than or equal to 0. And again, if you want to make an even stronger argument, if r is strictly positive, v double prime of r is strictly negative. The only way you can get 0 is if r is 0. And this means, again, that since r equals 5 is the only critical point, the second derivative test for global extrema imply that v of 5 is the absolute maximum of v for r greater than 0. And again, that's because v is concave down for all r greater than 0. So it's the same kind of idea. We have this volume function, and we've seen that at a radius of 5, we had this maximized value of 250 pi. We know that v of 0 was 0. We know that the function is concave down. And since this was the only critical point for r greater than 0, this has to be the absolute maximum for r greater than 0. This is an alternative approach to what we did on the previous page. You have to find the critical points in either case, But you have to make an argument that you found an absolute maximum by either making some kind of second derivative argument, or, like we did here, maximizing your function on a closed interval where that closed interval represents the natural range of values for the independent variable, or the natural domain of values, I should say, for the independent variable. You have to choose one or the other for any type of question like this. Again, this is because a critical point can be a local maximum, a local minimum, or neither. So these are natural types of optimization questions, and they represent a very common application of the type of math that we've learned in this differential calculus course.